what we're going to be going over. So today, again, the notes are going to be talking about the equilibrium math that we've been doing. And I, quite frankly, don't completely understand why this is in this chapter of the book. Besides the fact that we've now covered equilibrium on its own, we've covered equilibrium in terms of acid-base chemistry. So this is always at the end of that acid-base chapter when we start talking about what's called solubility product. I don't know if you have to write down a lot of what's on this first slide. This is me just kind of going over a justification of what we have to do. So maybe we just kind of not have to worry about jotting everything down. You saw again that solubility table with insoluble and soluble to begin with. It's not as simple as that. What we are going to be doing today is solving for K values. And just like in the first equilibrium we did, you had Kc, which was equilibrium concentration, Kp, equilibrium for pressure, and then in this unit we have Ka, equilibrium for acid, Kb, equilibrium for base. Now we have Ksp, which is solubility product. So how soluble is the product of these things? Now, some ionic compounds are very soluble, like NaCl. They don't really have K values, or they're large, kind of reminiscent of a strong acid or a strong base in that sense, where we don't assign K values to things that almost completely make products. So I give you a couple examples here on the board. However, our focus here today and next class are the things with small K values. You know it'll have a small K value if on the solubility table it says it's insoluble. So in Chem 1, when we told you, hey, play Battleship with the cation and anion, if it hits a highlighted I, that means it always makes it precipitate? If it's concentrated enough, yes. However, if it's not concentrated enough, it could actually be dissolved. So my last bullet point on this slide, again, is just bringing up that fact, that we're going to be dealing with things that have a very, very small K value. And what I can tell you is that this could be free response. Some of this math, they try to do it so you can do it in your head or on a sheet of paper, so it could be multiple choice. Since it is the last 2 days of this unit before your test, which is on Friday, I will have some of this on your unit test. However, I do not believe it's a major emphasis as opposed to a lot of the acid stuff, the buffer stuff. Boy, how many days do we spend on things that don't have a hydrogen in front of it and yet can act like an acid? So those are the things that you're more likely to see on the test, but there will be a little bit of this sprinkled in. And the hope is after today, the majority of the review guide you will be able to do content-wise, whether or not you get a chance to do it all. Again, there is one little thing we have to tweak onto this for next class as well, though. All right, so I'm going to move on to the next slide because, again, we didn't have to jot down much of this here, really. So solubility product is KSP. What I'm going to use for an example is silver chloride. Silver chloride might have been a precipitate that you made in the semester 1 project in Chem 1, where you had to figure out is it chloride or is it iodide. Oh, Kellen, I'm adding a new ion this year in Chem 1 semester project, bromide as well. Gives a slightly different color when in contact with silver. So now I can add like another 30 combinations to the possible guesses out there. I'm pretty psyched about it. Now, if you have a silver chloride solution with solid silver chloride in it, what my dash point here is saying is when you're at equilibrium, it doesn't mean that things stop. It means now the rate of the forward and the reverse reaction are equal. So if I give you this reaction, here's the solid silver chloride. At any given moment, there could be silver ions and chloride ions in solution that come together to form more precipitate. But if that were to occur, some precipitate would then dissolve and go back into the ion form. So what we're going to be dealing with today is things that make a solid, that we've talked about that are insoluble. Again, insoluble is a simplification. If you have a bathtub of water and a pinch of sodium or silver chloride, it will all dissolve. But in smaller concentrations or smaller amounts of solvent, it might not. If we were to solve for this using our K math, the solubility product for this reaction would be the concentration of the silver ion times the chloride ion. Does anyone remember the answer to my question on the bottom? And why are we not dividing by the silver chloride solid? And remember, solids, yeah, it's a pure substance, doesn't have a concentration. Remember, brackets means concentration. I mean, what's the molarity of a solid? I don't know. It doesn't have a molarity. Kind of like water doesn't. Just like weak acids and bases have K values that are known, these things have known K values. So in other words, if I gave you the K value for silver chloride, you could solve for the concentration. That's the type of math that we have to go over today. Okay, I'm going to give you one other example of this. How about one that's just a little bit more complicated? Magnesium chloride. That's how that expression would be written. Now, we do make assumptions when we are working with solubility products. We are assuming that ions behave independently of one another, which means if magnesium chloride were to dissolve, it would only become magnesium 2+ ions and chloride ions. We're assuming that those would not come together at all. And that's what my last hash mark in this slide is talking about. Which is why sometimes when we have experimental data versus theoretical data, our theoretical does not match up perfectly. We could have ions reacting with water. That would affect it as well. Remember, some things have that potential. Chloride typically would not, though. It's the conjugate base of a strong acid. Magnesium +2 or 2+. Usually your +2 ions don't react with water. It's the +3 ions that can make the water acidic. It's one of those Lewis acids, if you recall that. Again, I only really bring up the second bullet point because of that potential for questions on the AP exam dealing with here's what you calculated, here's what the reality was, give an explanation why. Sometimes ions do pair up in solution. After all, they are obviously charged particles, and if it's a high enough concentration in particular, the ions will be close enough to each other to make that pairing up. Bless you. So there's a couple of ways that we can solve problems with this KSP, this last topic. Next class, we're going to show you how to do this for double displacement reactions. After all, when you see those S's, maybe that's one of the things that comes to your mind. I could give you a problem like, let's say, magnesium nitrate plus sodium chloride in a double displacement reaction. Remember, they make the switch. Normally, you check your solubility table to see which one is the insoluble product. In Chem 1, if it made the insoluble product, you immediately assume, hey, a reaction has occurred. However, if they were in low enough concentrations of these different ions, maybe it wouldn't occur. And that's what we have to work on for calculation next class. Other ways we can look at it is just, hey, how much of this stuff could I dissolve in water before it creates a precipitate? So if I wanted to make a solution of something that is supposedly insoluble, what is the molarity that I could choose? That's the math that we're mainly going to go over today. However, the third way that we can look at this is going back to my front page. It had solubility curves on it. we could figure out whether or not a solution is saturated, unsaturated, or supersaturated. And how we would do that is by solving for the reaction quotient. So if a K value is known, and we gave you the initial concentrations of the different ions, you could solve for Q. Remember, we used to solve for Q back in the equilibrium unit to determine which direction the reaction would go to get to equilibrium. Kind of a similar thing here. Although in that equilibrium unit, I gave you the little shortcut, the little cheat of put K before Q and then put your greater than or less than sign, and whichever way it points, it's like an arrow to tell you which way the reaction goes. Here we might have to think a little bit. Sorry. Yeah, it's a bummer. So, if you remember that reaction quotient is products over reactants, however, we don't have to go over reactants for KSP values. So if Q is just like K, it's just not at equilibrium. If the Q value that you solve for when you have the concentration of your two ions is less than the K value, that means all those ions can be dissolved. It's an unsaturated solution. Or next class, when we dive more into the double displacement aspect of it, there would be no precipitate created, therefore no reaction. If Q would equal K, that would be the maximum amount of ions that could be dissolved before they start pairing up to make a precipitate. Therefore, if Q equals K, it would be a saturated solution. However, still, no precipitate would be made because that's the most that could be dissolved. And then the final scenario, well, if Q is greater than K, that means we have more ions dissolved than we should. So if we were looking at solubility curves, that would be a supersaturated solution. If we were basing this off of double displacement equations, that means a precipitate would be created. That would be your insoluble when you did your battleship in Chem 1. Yeah.
So in Chem 1 we have our lab where we heated it up, dissolved things, and let it cool down. So it was also dissolved and then crystallized. That's just different.
Remember, there's one thing that can affect K values, temperature. So when you had the same amount of solute in Chem 1, Abby's talking about the lab where you added a crystal at the very end and it just kind of exploded out. It went from supersaturated back to saturated because you overwhelmed the system and it even felt a little warm then. So the same amount, but then dissolved at a higher temperature. Yeah.
So once it goes back to a lower temperature,
it would. Once it went back, the way to make a supersaturated solution is you have to get it all dissolved first.
Yeah.
So that's why we had to heat it up to get it all dissolved. And as we cooled it down, then it was the same amount, but now it was, yeah. Because when you first added it in, and that first step of that lab, not all of it was actually dissolved. There's some sitting at the bottom.
Right, but so that would be a different scenario.
We'd have to say how much is dissolved instead of just how much is added. Because that's what was the difference in that Chem 1 lab, was that when you first added it in, there was plenty sitting at the bottom, but then by heating and cooling, you were able to get it all dissolved. And what you're going to see for this stuff is just going to tell you what's the concentration of the ions in solution at this moment. So then you'd use this scenario.
But if once we cool it down, the concentration of the ions would be the same as the higher temperature of
Yes.
crystallized.
Yep.
Which would mean our Q value would be greater than our K value, but all the ions are dissolved.
When we cooled it down, the Q was greater than K, yes. But when we heated it up, there could have been a different K. So the Q value would have stayed constant, I suppose, in that scenario that you're saying, at high temperature or low temperature, because the same number of ions. But the K value, because it's temperature dependent, the K value could have changed. So maybe the K value is different.
It's just special.
Yeah. Now, our old textbook kind of gave a roadmap of how we're going to solve this, because what I'm going to do after this slide is I'm going to go over two examples, one that goes in one direction on this roadmap, one that goes in the opposite direction. Molar solubility, well, solubility just refers to how much you can dissolve. If it's molar, then it's in a molarity unit. So sometimes you have to solve for the molarity of that solution. Solubility is more about the grams dissolved. So these four blue rectangles, it's kind of the path that we go about doing it. We could give you the grams per liter that could be dissolved for any of these things. And from there, you can convert to moles per liter, molar solubility. You could determine the concentration of both the cations and the anions from that. And if you know the concentration of the cations and the anions, you can solve for the solubility product, the KSP. So that's going left to right on these four rectangles. We could otherwise give you the KSP and have you figure out the solubility of that compound. So go in the opposite direction. So I want to give you one of both of these types of problems. Now my hope is by going over one of each type, I mean you did pick up two worksheets on the way in that could practice this. However, I also think that a lot of you are going to want to get going with the lab. So what we'll do is we'll go over these two examples, and then it'll be more of a, let's introduce the lab, let's have work time. You choose what you need to do. Again, there's two questions on WebAssign for you to answer between now and next class hour. I'm going to show you these steps again as we solve these two problems. So I'm going to move to the next slide. Okay. Maybe you don't have to write all this down. Maybe instead when I switch over to Smart Notebook, you just see how I solve this problem. But here is the first question that we're going to do. I give you the solubility of calcium sulfate. So in other words, calcium sulfate can be dissolved in water. However, it can only be 0.67 grams per liter. So this is probably something that pops up as insoluble on a solubility table. Technically, we can get a little bit dissolved. If I give you the solubility, I can ask for the KSP. Here are my steps to do that in. Again, I don't think you have to write down the steps necessarily. I'm going to switch over here and show you how to do this calculation in a second. But step number one, just like the blue boxes I showed in the bottom, we're going to go from grams per liter to moles per liter. We're going to do a mole conversion. Step two, we need to figure out the concentration of each ion. And finally, step three, kind of using that ICE method of equilibrium, and then what does K equal, we will solve for the solubility product of this particular compound. Okay? So again, this is the first type of question we could have. I think if you're jotting down something, the important part would be it's 0.67 grams per liter of calcium sulfate. That's what we're trying to solve for. And instead of writing down each individual step, which you already did on the previous slide, how about we just follow along with the work that we're going to do here. Okay, I'm given 0.67 grams per liter of calcium sulfate. First thing I want to do is get rid of grams and get that to moles. Moles per liter, molarity, that's your molar solubility. That's step number one. So I need to cancel out grams. Grams is on the bottom. Moles is on the top. We are doing a good old-fashioned mole conversion. You look up the mass of calcium, the mass of sulfur, the mass of 4 oxygens. That's 136.15. Because again, that allows grams on the top, grams on the bottom to cancel out. I'm going to carry 1 extra digit right now. So in other words, if the solubility of calcium sulfate is you can only dissolve 0.67 grams per liter, that's the molarity. That's the highest molarity I can make of that calcium sulfate solution. All right, Kellen. In every 1 calcium sulfate, how many calciums are there? In every calcium sulfate, how many sulfates are there? 1. That's going to make this problem a little bit easier. Because after my first step of solving for that molarity, what I typically do is I write down the expression just like you saw before. Now, what's kind of weird, and maybe you say to yourself, why in the world do I have to do this? Which I almost agree with you, and you might not have to. Again, this is a solid, so this doesn't have a concentration. Before this would even occur, you have 0 amount of both things. But then this is going to lose a certain amount. Let's call X. This gains X. This gains X. Because calcium and sulfate are in a 1-to-1 ratio, at equilibrium, the concentration of just the calcium should be the same value as the concentration of just the sulfate. Now again, this ice table thing you might not even really have to do because it seems kind of, well, yeah, duh, type thing. And I get that. The reason why I'm reminding you of this is whenever you solve for K, it's products over reactants. However, we've already established we don't have to go over reactant because that's a solid. So I just have to do the products, X times X. So when I solve for my KSP, it's going to be X times X. Let's see if I can get that in here. That X value is what we solved for right there. So we can take those X's and plug them in here. Take 0.00492 times 0.00492. So when we solve for the molar solubility, we're in essence solving for X. Now, if this wasn't a 1-to-1 ratio, it was a 1-to-2 ratio, well, then we'd have to adjust that a little bit. And maybe we'll see that on the next problem. That means if I were to solve for this K value, and now I'll go back to just my 2 digits, since the problem started with 2 sig digs. Remember, K values are unitless, but this would be how you start with solubility and you solve for K. Again, really the only math that we had to do for this is the mole conversion on the top, because then that went from solubility to molar solubility. Since it's a 1-to-1 ratio, that must be the concentration of the calcium, the concentration of the sulfate. And I know how to solve for K values. We've been doing that for almost a semester now. Questions on this path. Starting with grams per liter, solving for a K value. So my next question is the flip of that. So if I go back to my last slide here for a second. Here's what we're going to do to finish up notes for the day. is I'm going to give you the K value. And boy, copper 2 hydroxide must be really insoluble. After all, look at that KSP value, 10 to the negative 20th. Not much of that can be dissolved in water. We're going to figure out how much can be dissolved in water, because that's what solubility is. How many grams can be dissolved in a liter? So we're going to do the exact opposite steps. And again, I don't think you need to write down the steps. Maybe just write down copper 2 hydroxide and the KSP value so you know what we're starting with. And let's go over that path of how to solve this type of problem. By the way, in my step 2, I say that S. Some textbooks, instead of in your ICE table having an X, they'll say S for solubility instead. I don't know, isn't X the variable in any variable ever? But for some textbooks, they like to switch it up and say solve for S in your ICE table. Nah. All right, so in this one, we have copper hydroxide solid, copper 2 hydroxide, and it gives a K value of, what was that value? 2.2 times 10 to the negative 20th? Sorry that I ran out of space there. In the dissolving of copper 2 hydroxide, there's twice as many hydroxide ions present as copper ions present. That's all that I tried to show there. And an ICE table is just a way to organize what you're about to do. And hopefully by now we realize the importance of organization when we do our math in this class. So that's all that I was showing you. That 1 to 2 relationship. In an ICE table of any type, we have to take into account the coefficients. That means if I were to solve for K, it would equal X, the concentration of the copper, times 2X, the concentration of the hydroxide. And what should I do to that 2X? Square it. Because you always have to raise it to the power of the coefficient. That means if I extend my page here a little bit, KSP would equal 4x cubed. That's a horrible X. Didn't make it better. Yeah. And if you're given the KSP value, like we were at the beginning of the problem, 2.2 times 10 to the negative 20th, we could solve for X. Divide both sides by 4, take the cubed root. I get 1.8 times 10 to the negative 7. What does that number mean? That is the molar solubility. How much copper hydroxide could be dissolved. That's the molarity. If you wanted to make an actual solution of copper 2 hydroxide, that's as strong as it can be according to that K value. 0.0000018 molar. I mean, that's a pinch in a bathtub size of water. However, this question wasn't asking for molar solubility, which again, I can just give a capital M for that. it was asking for solubility, which solubility is grams per liter. So the last thing I'm going to do to this problem, remember that's your moles per liter. I'm going to use the periodic table to figure out copper 2 hydroxide is 97.57 grams per mole. So if I do this calculation, I get 1.8 times 10 to the negative fifth grams per liter. So in 1 liter of water, if I can get 0.000018 grams of copper 2 hydroxide, that's how much can be dissolved in that. That's why that one has an I on that solubility table. Now again, the practice problems that you picked up, one was an old AP sheet from years ago. The other one was just practice problems that I found from a textbook once upon a time. That I would say we don't have to worry about right now, but you're going to see 2 questions like this on WebAssign.